Good afternoon, everyone, and welcome for my thesis defense. Thank you for turning out in such large numbers. I'm here to talk about my project and my thesis topic, the performance evaluation of the CNF routing protocol in multi-hop wireless subnetworks. This work has been done under the guidance of Dr. Ray Chaudhary and is a joint work with Shweta Jain. Let me give you an outline of the talk. I start with describing you the CNF architecture. Then we'll go over to the routing protocol, which is my contribution to the thesis. I will walk you over my implementation on orbit, and then we'll see what results we got, and we'll go over the summary and future work. Internet usage, we know, has been growing drastically, and a large number of these end users are now mobile clients. With the proliferation of smartphones, and iPhones and netbooks, a lot of content is being delivered to these mobile end users. With mobile end users, disconnectivity is a common inherent characteristic of these networks. Connection-oriented models like TCP do not really work well in these scenarios. Disconnection these days is a reality, and TCP was mainly designed for wired networks, and it always assumes that an end-to-end path is present. Clearly, TCP does not address disconnected networks, and so it fails in these situations. So here we present the cache and forward architecture. This is a clean slate network. This is the clean slate architecture, which is mainly for mobile content delivery. It comes from the hop-by-hop school of thought, which can tolerate disconnections and network partitions. Wireless links are time-varying in nature and are unreliable. A lot of packet losses happen, and MAC retransmissions and a wastage of resources take place. To minimize these wastage of resources, we consider opportunistic transmission. What do I mean by opportunistic transmission? We transmit a packet only when the link is good or when we think it is good, and try to optimize the network throughput instead of an individual flow throughput. We also bank on the fact that memory is getting cheaper by the day. So if you look at this graph, we see that a megabit of memory cost a couple of dollars back in 1991, and it is almost a few cents right now. So we propose this idea of embedding a lot of memory into routers that we're proposing. So this is in-network storage. So instead of caching a lot of data at the edges and at the end servers, we propose that data would be cached within the network. So content retrieval from the network is much faster than going to the edges and retrieving data. This is a protocol stack for CNF. The first is, let's talk about the transport layer. The main function of the transport layer is to provide a hop-by-hop transport. It transfers a file from one hop to the other completely reliably. Traditional features like flow control and congestion control are delegated to the lower layers here. Second is the network protocol. The network layer takes care of the routing. As I just mentioned, that we have a lot of memory embedded in routers. So our routing is storage aware, and it also incorporates the opportunistic transmission that I mentioned. Flow and congestion control is also taken care by the routing layer. Last is the CNF, then is the CNF link layer, which takes care of reliability and error control. It sends packet batch-wise and takes care of retransmission and ACKs and MACs and so on. Every file that goes through a router will traverse this entire stack. The control plane consists of a few services, few services or applications which is going to help CNF. The first is a content name resolution service. So whenever I mentioned that we're going to be caching and storing packets with files within the network. So whenever we need to find the location of these files, we go to the content name resolution service. If a requester needs to know where a particular content is placed in the network, this service will, based on some hashing algorithms, and it will resolve which router is the content located. And then is the cache management protocol. If you're talking of caching and storage, we have to talk about cache replacement algorithms. This is where the cache management protocol comes in. Based on popularity of the content and various other algorithms, we decide which content gets replaced and which content gets cached where in the network. Let me just go over the same thing through an animation. Here we see is this is a CNF router. It has 3 layers of storage in it. First is a link layer buffer, which is the buffer we have in our routers currently. The next is the network layer storage. So when I said opportunity transmission and the fact that we store and send a packet only when a link is good, we'll be storing it in this network layer storage. And the third is the application level cache, where all your popular content and caching will take place. Suppose we are sending a piece of data from the media server to the mobile client. We see that the file is transmitted hop by hop up to the last hop. If the last wireless link is bad or say temporarily disconnected, we store the packet within the router. This is stored in your network layer storage, and once the link improves, you transmit the packet forward. While you are on router 2, suppose router 2 thinks that this content is very popular and probably will be requested again. It promotes it to the third layer of caching, which is the application level cache, and it triggers off a cache management and CNRS service, which will update its servers and let all other routers in the network know that it has cached this content. So next time a request comes for the same content, it can probably be serviced right from this router instead of going to the media server. Let me now brief you about the routing protocol. We studied a couple of existing routing protocols like OLSR and AODV. So OLSR is a proactive routing protocol which exchanges messages to know the topology information and maintains routing tables. Unlike OLSR, AODV is a reactive protocol which only when a content has to be transferred, a route discovery takes place and the route discovery is on the fly. In such a case, if say I'm transmitting a file from X to W, I will choose the path as shown in red. The numbers there represent link cost. So if suddenly one of these links go bad, the current routing protocol will still transmit on the same link. If there's another flow going parallelly, which is in the same channel and in the same vicinity, it will cause interference to the other flow and cause its throughput to drop as well. The design issues for our routing protocol. The existing routing protocols have a lot of overhead because links keep changing frequently, and they do not maintain a history of how the link has been behaved. So they might trigger a route discovery unnecessarily, or maybe a route can just get repaired even before the route discovery takes place. The content that we're transmitting here is in the order of a few gigabits. So if you have to transfer 1 gigabit of data over a 54 Mbps link, it takes about 150 seconds, whereas over a 5.5 Mbps link is of course 10 times higher. So instead, if I've traditionally had a good link and I've been standing at 54 Mbps and my channel suddenly goes bad and it drops down to 5.5, I don't need to set it at 5.5 and cause interference and throttle other guys' throughput. I might as well wait for some time and then when my link comes back to 54 Mbps, send it later. So the other traffic in the network will not get affected and you'll not lose out on, you'll eventually have a good link and transmit better. These are a few parameters that we have considered for our routing protocol. First is the storage. We consider how much storage is available in all other routers in the network before we make a forwarding or routing decision. Storage here is also an indication of congestion control, congestion in the network. So if a router has very little available storage, it means that there is a lot of congestion in that area and we might avoid those routes. Second is the short-term cost, which is nothing but the instantaneous value of your metric. And the last is your long-term cost. So long-term cost is a historical representation of the link. What I mean by historical representation is it tells you how my link has behaved in the past, and where it just tells me how my link has behaved in the past, and whether and we assume that the link will still behave in the same way in the future as well. So at least for this implementation, I'm considering my long-term cost as an average of my past n short-term values.
So you write in the bullet, it's a moving average over the short-term sliding window. So why is it not a long-term sliding window if it's a long-term cost?
I'm just averaging over the past n samples of my short-term.
Okay, so you're taking the values you call your short term and averaging some past history of them?
Yeah.
But the window you average over is a big window?
Yes.
Okay.
So it's the short-term window that I'm averaging over. Like the size of the window is big, but
it's a
the values
long-term window of short-term values. Is that okay? All right.
So this is the forwarding. This is how we make our forwarding decision. There are three regions that we consider: stable region, store region, and forward region. The stable region is where your short-term costs and your long-term costs are approximately the same. That means that the link is approximately been behaving how it was in the past, and it is a good time to transmit when we transmit data. The second region is the store region. It says that my short-term cost right now is really bad, it's really high, but my long-term indicates that, oh, this link has been pretty good in the past. So I might as well store the data right now and transmit later when I will have a better link. That's why all the packets in this region will be stored. The last is the forwarding region. This says that my long-term cost has been pretty bad, but right now I have a very good link, so I make the most of it and apply my opportunity transmission here, and I decide to forward my packet. There's one check I made before forwarding the packet. Is I just check if I have some minimum available storage along my downstream path, so that in case there is a disconnectivity, I do not have to drop the packet and I can store it within the network. To quantize these costs, we studied a few routing metrics. The first is the hop count, which is a very simple primitive metric. It does not consider any link variations or underlying channel conditions. Second is the ETX, which is the expected transmission count. It is the number of transmissions required to successfully transmit the packet. It does not represent changes in physical rate. What I mean by this is, even if it's a 54 Mbps link or a 5.5 Mbps link, as long as the packet losses in the system are constant, the ETX will not change, it will be the same value. And the last is the ETT, which is expected transmission time. It is calculated based on ETX and the bit rate. So this will give you different values based on different bit rates being used. We use ETT for all our calculations and routing metrics. Let me give an example of how routing will happen. First, this is a simple scenario when I'm just sending a packet from S to D. As you can see, both the short-term and long-term costs on both the paths from A and from G are the same. So I randomly choose G to send the packet through. Once I reach E, I see that my link ahead has broken. So I decide not to forward through F, and it will go through B. This is how any traditional routing protocol would work. Suppose I have another packet to transmit from S to D. This time it will go to B. Once I reach B, I know that I see that both my next hop links have suddenly increased. But from the routing table at B, I can see that my long-term cost is short enough. That means it says that this link has always been good and it has a cost of 65. But suddenly right now it's just increased to 110. Maybe there was some noise spike or some congestion because of which this happened. So I decide to store the packet. I will not transmit it on either of the links, and I will store it till the channel conditions improve. And once when the link condition improves, I will send the data over. Some alternative approaches to the two-dimensional forwarding space that I mentioned. Actually, first, the way I'm calculating my long-term cost right now is just a mean of all the averages of my short-term cost. Instead of mean, we can use the mode, which will probably be a more accurate indication of how my long-term behaved instead of the mean. We can use some predictive algorithms like machine learning and, to predict what the short term will be or what the link would be in the future. So if we are able to predict accurately how the link would behave, we can optimize our routing decision and store or forward the packet accordingly. We can also weigh link cost and storage based on proximity from the source or destination. What I'm trying to say here is, if there is a disconnection or some bad channel which is 10 hops away from me right now, or which is 10 hops away from me right now, it should not influence my decision of storage or which path should I take at this end, as much as if there is a broken link just 2 hops away from me. So we can wait based on how far I am from the source, from the destination. Another way of doing this could be opportunistic routing. We transmit on the fastest outgoing link as long as the long-term path quality is reasonable enough. This is like a greedy algorithm. You choose the fastest neighbor, and as long as through that neighbor you are able to reach your destination in some reasonable long-term time, you can transmit over that path. The last is a unified metric which can combine both link cost and storage, and you can run a Dijkstra's algorithm on that and just choose a minimum cost path. The scheduling algorithms that we use in our router right now is just a round robin algorithm. There are 2 queues. One is the link layer buffer, and the next is the network layer buffer. I'm implementing this round robin algorithm only on the network layer storage. It just checks for every packet whether it has a path or not, and if it has a path, it will be enqueued in the link layer storage, link layer buffer, and whatever algorithm is running in the link layer will take care of transmitting the packet. Let me now walk you through how we've implemented this on Orbit. We need a basic topology discovery protocol and a message dissemination protocol, which will tell us about all the other nodes in the network, about how much storage all the other routers in the network have. A lot of popular routing algorithms do that, and we found that OLSR is a very robust protocol which exchanges hello and TC messages, and it gathers all the information about the entire topology. Based on it, it calculates its topology tables and then runs Dijkstra's algorithm to find the shortest path to any destination. So we use this OLSR and added our own fields to OLSR to make it compatible with what we wanted. The fields shown here in blue are the fields that we have added to the original OLSR packets, so that it can also transmit the data that we want. So we now have these new topology tables, from which I know the storage at every other router, the short-term and long-term costs to every other node in the network. We run Dijkstra's on this new table, and we get a short-term path. For this short-term path, we calculate the long-term path and what the minimum storage is for that particular path, and we calculate the routing table as I've shown in that figure. For a complete evaluation on Orbit testbed, we need a complete protocol stack. So to compare with TCP, as I mentioned, that CNF has a hop-by-hop transport protocol. There is this project being done in UMass, and they have proposed this protocol called HOP. It is conceptually very similar to CNF. It also to the CNF transport protocol. It imbibes the hop-by-hop principle, and it provides reliability at the transport layer, instead, as opposed to how we have proposed in CNF that we have reliability at the link layer. So for this implementation purposes, we have disabled all the retransmissions and reliability from the link layer. And this code is open source. So we have used this code and integrated it with our CNF routing protocol. This is how the software modules interact with each other on the Orbit testbed. So hop and OSR talk to each other through the kernel routing table. We write whatever our decision, whether it's store or next hop or whatever the next hop is, and hop just reads it from the kernel table. We modified the MAD Wi-Fi driver and did some hacks so that we could emulate packet losses, disconnections, and emulate mobility on Orbit. Experimental setup. We used the radios on the 802.11g mode. They were all running on channel 11 at auto rate. To evaluate TCP and UDP, we used iPerf. Most of the traffic patterns we used were either Hosanna arrival or CBR, a constant bit rate. We used IP tables to emulate time-varying links, create topologies, because all the nodes in orbit are within communication range with each other. So to create disconnections and topologies, we had link layer filtering. The window size that I'm calculating my long-term over is 3,000. That is, I'm taking an average of 3,000 samples of my short-term to calculate what my long-term is. And the storage threshold is 4 times the file size. That means if a router already has 4 files stored in it, I would not prefer that router. I would prefer a router which has less files stored over this.
So long term is 3,000, like in some.
3,000 value, 3,000 seconds.
And how? Oh, so the short term is every second, and it's 3,000 seconds. Yeah. It's like 45 minutes or something.
So we measured the throughput for the topology given here. We had 3 flows from S1 to D1, S2 to D2, and S3 to D3. The file size was 500K, and we transfer 100 files in all. We measured the average throughput for this file transfer. We can see that CNF saturates at almost 1 Mbps higher than TCP. This is mainly because of the store and forward that we say. So every time we find a congestion, we back off and store the packet for a longer time and send the packet only when the congestion has decreased. So we end up retransmitting a few number of packets, and that's why it's good.
So in your experiment setup, what is the long-term cost trying to capture? Like what's changing, like the cost?
In this experiment, there's nothing changing.
Okay.
So in this experiment, we don't need the long-term.
So in general, when you say 3,000 seconds of long-term cost, like you average it over 3,000 seconds, what's it that you're trying to capture? Like?
If there are some sudden disconnections, so basically I did a mobility experiment later, in which I cut the link for some 10% of the time. So in that 10% of the time, my short-term cost is very high, but my long-term was pretty decent. So I decided that I will store the packet because I knew that it would. The long-term says that it has been good.
So in the real network, like what do you expect? Like it's the typical time routers, you know.
That is an open design, open question. It's like a parameter over how long a time frame do you want to capture the long term.
Yeah, because if you're talking about wireless links, 45 minutes or so is a very, very long time, right? Like you're talking about mobiles that are moving. So I don't know whether, unless you're talking of, I don't know, something to do with a cellular tower where some metric might not, I don't know.
So in this experiment, right, like you varied the offered load by changing the arrival rate of the file.
Yeah.
So like the 5 megabyte bits per second, is that megabyte or bit?
A megabit.
So it's like 10 files per second of 500 kilobytes, something like that.
Yeah.
And then you ran this for, is it 100
105.
transfers in total or 100 per session?
100 files and all. Like
Per experiment.
Per experiment, per value.
So the thing only ran maybe for 20 seconds or so, right?
Yeah, I'm transmitting only for 20 seconds, but to reach the resolution it takes a little more.
Okay. And the throughputs you get are total throughputs for the
Network,
3
total
sessions?
network throughput over the average over all 3 sessions.
No, averaged over, it's per session throughput, averaged over the 3 sessions, or is it the sum of the 3 session throughputs?
It's a sum of, you mean 3 flows, right?
Yeah.
Yeah, it's a sum of the 3 flows. Because the way I'm calculating my offered load is the sum of all 3 flows.
So you're clearly like sort of your TCP is falling apart at 2 megabits, right? So what exactly is sort of happening in the network?
I'm overloading the network, I'm saturating the network for more than what it can handle.
Yeah, so where do you think that you see the problem? Like when you say you're saturating, where in your network do things go wrong?
So everything is going through, all these flows are going through this one central node initially.
Yeah.
So it is oversaturated and this takes a lot of time to transmit the packets. This is basically the bottleneck, and in our CNF case, once this becomes a bottleneck, we just change and we start sending packets through here, because we know that the storage threshold here has increased.
So even so in this example though, there's no rerouting, right?
No, it happens. It's per
Even
packet.
in this baseline example, you're rerouting things.
Yeah.
You're not just using the fixed routes.
No, I'm not using the fixed routes, I'm rerouting.
So it seems like then 100 files isn't enough to sort of talk about your averages, right? If you're gonna be busy changing, so the routes change at some point, 5 or 10 files or 50 files in.
Yeah, once there's a lot of traffic accumulated at this central node, the routes change and they start going from here.
So when you have this sort of overflow situation, where exactly are the bottlenecks forming? Where are the packets are being dropped somewhere? Are they being dropped?
Yeah, and TCP has congestion control, so it starts pumping data at a lower rate as well.
So, I mean, it's so if somebody says, oh, I have a traditional network and it's TCP, I sort of have a sense of what's going on, right? But with this fact that you're running this network, these very large buffers, right? I have a hard time sort of getting a sense of where the packets are accumulating, and are things just accumulating, and for instance, you just sort of store things up and then after 100 files, you just stop and let the thing gradually empty out and then calculate average rates based on how long it takes? Or, because with all this storage, there shouldn't be anything dropped anywhere.
So there are no packets being dropped, but it spends a lot more time in storage. So packets have been dropped in the TCP case and not in the CNF case.
Is that clear, that things are dropped?
Because a lot of retransmissions happen. Because of the bottleneck here, all 3 flows go through this particular link. So at the MAC layer, a lot of...
If you want to interpret the number, 2.5 is about half of 5.5 megabit. And because of all the interference around that node, the rate drops to 5.5 and you get about half that with TCP. With storage, it gives you a bit more margin because you spread the traffic around. But I think you're right that you need to do this for 1,000 packets or so too.
So do you agree with him? Is that what's happening?
Maybe the time frame is too short, so I...
No, do you agree with him that his sort of TCP is getting you about half
of 5.5.
So that's a previously observed result for mesh kind of situation.
Next.
But this buys you some gain, but not, it doesn't solve the problem.
So I have a feeling that your congestion is not actually changing when you're switching to those routes. As you said, these are all in the same range. I mean, the illusion of doing link sort of like on packet filtering doesn't change the fact that your congestion is still there. Like, why does it make a difference? It might make a difference because if you are doing not retransmissions with the MAC, and you might have a different strategy of bundling packets and all. But in terms of congestion, it should be the same. I mean, the bottleneck you're showing there, if these were sort of like a multi-hop network, I would have thought that, but can you elaborate on that?
I didn't get the question.
I mean, once you have 3 parallel flows instead of that one single sort of like bottleneck,
Yeah.
so you're saying the congestion, now it's not bottleneck anymore because you have 3.
There is one flow which is still going through here,
Yeah.
but some packets will now be transmitting through transmitted.
But
through
they all are in
here.
the same contention
same.
range, right?
Oh yeah.
So it doesn't actually change the bottleneck situation at all, or does it?
It doesn't, but this router has a fewer number of files to serve.
So you're saying
So-
the queuing is actually,
At
the processing
at
of the packet is actually bottleneck,
It's
that's
faster.
what it was.
Yeah.
So somehow the auto rate went to 5.5. Is that what you're saying?
For 8 to 11G, I think.
But somehow that's just you're kind of, like that's a failure of the auto rate, right? Like the auto rate ought to have stayed at, 50 something,
Okay.
shouldn't it?
No, because I don't know how auto rate, on what basis auto rate changes.
Just that the real channel is still, that next node is just 20 feet away, right? So it should have, like somehow, like, I mean, the fact is this happens, right? But the auto rate shouldn't have done that, I don't think. Just because of
So in your defense, I would say that she was working mostly on routing and we just rolled it to this network. I think the in-depth understanding of auto rate for this environment is quite complex. So it is whatever auto rate
but, yeah.
But I didn't ask her to study the auto rate issue.
The auto rate experts would agree.
Whereas Kishore.
I want to know what auto rate does.
No, but it shouldn't have gone to 5.5
Yeah, so basically-
because the channel was always in the orbit.
So if it sees a lot of retransmissions, it reduces the rate.
That's the
So if there is a collision, then it considers as a channel failure or bad channel. That's right.
But definitely if you are aggressive in keeping the rate up, the net system behavior is better.
Yeah, at least in this kind of example. So you have more slides?
Yeah. But she will leave unresolved.
I'm just teasing her. But somehow you're calling these baselines, but you're doing, usually a baseline is like you're not doing too much. Like, so, but I always thought the baseline was you don't do any adaptive routing, you just set the 3 routes and that's the baseline,
That's a misnomer.
So I guess she has more complex results.
Yeah.
Yeah.
I have much complex
So she
scenarios.
was
Scenarios,
she was working first with things baseline is pretty complicated.
Right.
Okay, so the whole thing comes on me now.
This is the same, the parameters for this experiment were same as the one before, and in this case we're measuring the packet loss ratio. We're comparing UDP with CNF. I did not compare it with TCP because I don't know how to measure the number of retransmissions in TCP. We see that that UDP drops a lot more number of packets than CNF. CNF implicitly does flow control, so whenever I see that there is that my GT in the next hop is high, I store the packet instead of transmitting, and that's why we have less number of retransmissions as compared. Well, UDP does not have retransmissions; it's an unreliable protocol, but we drop less number of packets as compared to CNF.
How do you distinguish between packets that are dropped because of MAC layer contentions and packets that are dropped because the queue is full? Do you distinguish or does this capture both?
So if at least in UDP case, I don't know where the packet was dropped. IPerf just gives me a result of how many packets I received. And in the CNF case, I'm just counting how many number of retransmissions did I have to do. So I really don't know where the packets happened.
So symmetry combines both things together. I guess this goes back to Ali's question, right? So as you increase the offered load, do you have a way of figuring out whether the thing is saturating because of MAC layer contention?
No, I don't know. I just know that the packets are being dropped somewhere below.
Is that really your definition for CNF of the loss ratio? Because like, it seems to me that like it's best at 0. Like somehow shouldn't it be successful transmissions divided by total to get something? Like your UDP, your ratio is bytes received, which is a success measure, divided by bytes, total number of bytes transmitted. Like,
yeah.
well, the other one is like it's the bad thing divided
Yeah,
by the good thing,
yeah, I
whereas
think
the first one is the good thing divided by the
Minus
total
that.
thing.
Yeah, I think it's total number of transmissions minus the number of transmissions I was supposed to have, divided by. I mean, this is the number of. It's a good thing. The number of packets that I received over the total number of packets that I sent, which includes by the number of retransmissions.
So can you compare? Are they really the same measure? Can you compare the two?
They are the same measure. What I've written, the formula is wrong. I'm sorry for that. For the next experiment, we changed the underlying channel conditions. That is, we dropped. This is where we dropped packet at the bad Wi-Fi level, and we see that at more than 5% packet loss, TCP completely fails. At around, in fact, 6.5 to 7%, TCP just cannot transmit a single file further, whereas CNF is much more robust to losses in the network. We also can see.
So I think you could point out that earlier TCP studies with mesh networks have shown 3-4% as the threshold for this kind of thing.
For what?
And this was for linear topology.
This is for the topology shown here, the linear topology over 3 hops. Next, I'm just changing the number of hops in the network. So I just see the effect of varying hops. So first, I'm transmitting to D1, D2, D3, and so on. From this, one observation that we can make is the file size does not have a very significant effect on the performance, and that the performance degrades as the number of hops increases.
So they're all within the same contention region, right? All these
Yeah.
nodes. So this should definitely contain an effect of that MAC layer contention, the MAC layer contention, not because of
Yeah, it's just a linear topology in the rock.
So I think we are being a bit unfair to TCP, right? Because TCP is confusing wireless errors to be because of congestion and the typical TCP problem, right? So maybe we should evaluate with TCP that takes care of that kind of thing. Like a lot of study has been done trying to alleviate that problem of TCP, where wireless errors are considered to be router congestion and so on and so forth.
So this whole CNF is proposed
No,
for that TCP which has its battery.
Right, the deal is that if CNF probably requires a lot more of changes to the internet or the network in general, then probably TCP with those kind of fixes will. I'm not sure, I'm just saying maybe it's worth evaluating. It's not clear that here TCP is actually suffering a lot because of that problem it has, which everyone knows. Like it's not that you're also saying the same thing, but probably would make sense to.
Changing TCP is not easy either, but of course CNF as an overlay is about the same difficulty of deployment. As changing TCP may be even harder.
Okay.
Next, we connected.
So are you using a one-link flow control for the CNF? Yeah, for instance, you could be like, oh, for each hop, I'll do TCP for CNF. Like you have to have some measure for.
I'm running it over UDP, so for every.
So you're doing UDP,
UDP.
but you could have done TCP for each hop if you wanted to.
Yes.
Yeah. Do you have any sense of how the results would vary?
Can try the picture or do that. In this scenario here, we did an on-off scenario. So basically the link was on for 90% of the time, and for 10% of the time I dropped all packets at the link here. We had a constant bitrate traffic, and I'm measuring the average streaming throughput. Average streaming throughput is the throughput I got per packet and not the overall network throughput. And we see that, so when there was no connection, TCP completely fails. All those files transmitted in that period of time got a zero throughput because the connection could not be established. And CNF performs better in these cases as well. The last we experimented with the DTN kind of a scenario. We just wanted to, with this experiment, all we wanted to do was prove that CNF works even in case of extreme disconnectivities. Consider these two clouds A and B. All the nodes within these clouds are connected to each other, but they're not connected to the outside world. And there's a bus running from A to B every 6 minutes, and it stops at every cloud for a minute and it comes back. So this is like a message ferrying system, and it's the only point of connection between both in both these clouds. The values there, we transmitted around 8 files, and these are the values for the file delay and throughput that we got. So this experiment, all we're trying to say is CNF can perform even under conditions of extreme disconnection. To summarize, we designed and evaluated the protocol evaluated the routing protocol and implemented a small network prototype on Orbit. For static scenarios, wireless multi-hop static scenarios that I showed, CNF throughput is around 70% higher than TCP. And especially with mobility and channel losses and packet losses, CNF has much better throughput as compared to TCP. And for future work, we can compare R2 dimensional metric with the different algorithms that I mentioned before. We are work in progress right now is the complete full-featured CNF stack with all the content addressability and caching and content and resolution services that I mentioned. And then we can compare our entire stack with the TCP stack. We can try a few more experiments with mobility, traffic models, and eventually we are planning to integrate it with the WiMAX base station present in lab, and probably perform a few more experiments with the mobile vehicle units. Questions?